Today we're going to talk about angular quantities, and we are going to deal with systems or objects that are not translating but are rotating, like this top. Now here's the difference. This, watch it, this is translation, right? It's translating. Oh, look at that up and down. This is translation. That's a kind of motion, translational motion. In other words, the object isn't changing how it's oriented in space, it's just changing where it is in space. Ooh, yeah, translation. But now, if I make something spin, it doesn't translate, or it translates a little tiny bit as it travels along. But there's a lot of motion here. And this motion is along an axis, what we call an axis of rotation. So if you look at this top, imagine a line coming out of the paper through the top and then aligned with this pencil. Okay, coming out into space. That's the axis of rotation. And the object isn't changing shape or anything. We're going to not change the shape of the objects that are rotating. Now this is rotational motion. Oops. Rotational. And lots of things rotate, right? Bicycles, bicycle tires. You translate and rotate as you roll along. We'll deal with rolling motion too later on. And what we're going to do is we're going to define all of this stuff. This is what the lecture is going to be about. So there's everything you need to know right here. We're going to define all these quantities. So this lecture there's a lot of stuff. It's not very hard. There's just a lot of it. A lot of quantities and variables that you need to learn. And it's very similar to what we did when we talked about rotational motion or translational motion, right? When we dealt with translational motion, we dealt with position. We dealt with change in position or displacement, velocity, acceleration. We're going to deal with all that stuff, but instead it's going to be angular position, angular velocity, angular acceleration. And they have their own units, and there's a few equations and stuff. So let's get started on that. So let me draw this shape right here. Oh, you know what? Maybe I'll trace it. Ooh, that'll be. I don't know if I can trace it. Well. Pretty close. All right, so there's our top. Here's the circle that we're going around. Here's the center, right? Or somewhere around there's the center. Now I drew a little dot here on the edge. See this little dot? And I'm going to rotate it up like that. I want to know, okay, what is the position of this little dot on the edge right here on the outside lip of this little top I have? Well, it's right here. And when we describe position, right, in polar coordinates, well, we would need an x-axis and a y-axis. And then we would describe, oh, this thing has a radius, doesn't it? But it also has an angle. Okay, and this angle, I'm going to call this theta. This is going to be the angular position, theta. And it's just where it is in terms of how far it rotated from some arbitrary positive x-axis. Kaylee Lee. She's right there. Now, let's say it was right here to begin with, but then it's spinning. This object is going to be spinning. Oops. Oh, I can't make it spin. There we go. Well, let's say we look at it over a short period of time. So this is the initial angular position, but then we wait a tenth of a second or something and notice that it's right there. So we have a new position. And that new position, it has a radius. Now the radius hasn't changed, right? I mean, the length of the radius hasn't changed. But theta has. Well, now here's our initial angular position. We'll call that theta sub I. That's the initial angle. Well, what about this? Here's theta final. So we changed our angle. So we call that a change in angular position. Sometimes we'll call that an angular displacement. And we're going to call it delta theta. And delta theta, by definition, is the final angle minus the initial angle, right? Just like we've done for all delta quantities, right? Make sense? Like, you know, what if this were 70 degrees and this was 40 degrees? Well, then this would be 30 degrees, right? You just go 70 minus 40 is 30 degrees of a change in angular position. Now, I put this little dot on the outside, but notice that the angular position, it would be, the change in angular position would be true for any dot along this line right here. Because it's a fixed, rigid object. Now, we have a way of measuring angle. There are several ways of measuring angle. Okay, so how do we measure an angle? What units do we use for angle?
Degrees.
Degrees. That's the one we're most comfortable with. I like degrees. There's two more though. There's another way of measuring angle that I think you've used in your math classes. Radians is another way of measuring degrees. And then there's one that you've used many times, but you might not even think of it as an angle. Okay, and what is that? Look over here. What is another way of measuring angle? It's not degrees, it's not radians. What would I use for something that was spinning really super fast, you know? All right. Would I use? I'd probably use, now you might, rotations? You said revolutions? Okay, I can't hear anymore. So yeah, revolutions or rotations. Now, let's suppose that this thing, you have a little spot on here that we're looking at, and it makes one complete rotation. One complete rotation. Okay, so that's one rotation, rot or rev, if you want to call them revolutions, and I will call them revolutions. Well, how many degrees is that? You know that. How many degrees to go around once? 360 degrees. And you probably remember how many radians there are going around a complete circle. 2 pi radians. You remember that? 2 pi radians. And I'm going to use the word rad. That's how I'm going to abbreviate radians. But do you remember how radians were defined? Actually, radians are a really cool unit to use to measure angle, because it's a measure of how much angle you've swept through, wrapping in terms of a radius wrapped around the outside or the arc length of the circle that it's going around. For example, take a look at theta initial. This has got an arc length to it, doesn't it? And I'm going to call this arc length S. And then here's R, which doesn't change. So we went from 0 to this position, this angular position. And so to measure the angle in radians, we go S over R. The arc length over how long the radius is. Now this might be half a radian, right? If I took half a radius, about this long, and I wrapped it around there, how much angle would it sweep through? Well, then it swept through roughly about half a radian of angle. Well, what if you took a full, what if you had 1 radian? Well, you take a radius and you wrap it around, and that's almost a little bit more than a radian, I think, that I drew here for my final position. And I think you know that it's just a property of our universe, that if you take the radius of a circle and you count how many times you wrap it around, you go 1, 2, 3, 4, 5, 6, with a little bit left over, like a quarter of a radius left over about. Well, it turns out that 1, 2, 3, 4, 5, 6, and a little bit more is equal to 2 pi. I mean, pi is how many radiuses wrap around from here over to here. That would be a pi radians, right? So it's based on the circle, which is really nice. 360 degrees, that was pretty arbitrary, right? You could have picked any number to divide it up in, but they picked 360 because 360 is easy to divide up into ninths and quarters and halves and stuff. Anyway, this is how we define the radian, measured in radians, which I'm going to call rads. Now notice a radian is a dimensionless unit. Arc length is measured in meters. The radius is measured in meters. You have meters divided by meters, which is dimensionless. But I still call them radians. It's kind of a phantom unit, the radian. It kind of appears, but it doesn't contribute any units to your answer, as we'll see. So if I take this equation, we've got the first equation I really want you to know is that the arc length, that is the distance traveled to get to that angular position. S is the distance, right? S is not a displacement. S is a distance. It's how far you've gone from here, traveling around this path to here. And that's going to be equal to R times theta. But theta has to be in radians. Okay? So this is an equation you need to know how to use. Now notice something here. Like this was S initial, and then here's all the way out to here, from here to here, that'd be S final. If I go S final minus S initial, I get delta S, right? Delta S is from here, the arc length from here out to here. So I'll call that delta S. And so delta S is equal to R times, well, from here to here, that's delta theta. So this is another equation I want you to know how to use. The change in arc length is equal to the radius of your circle times the change in angular position, but your change in angular position, your theta, has to be measured in radians or this won't work. This is all based on radians. Now, some of the stuff we're going to learn works in degrees and it works with rotations. But some of the stuff that we're going to do only works with radians. So when in doubt, measure your angle in radians. You can't go wrong with radians. Radians always work. Okay. Well, if I have a delta S like this, if I have, this position and I'm going to rotate to this position, it takes time to do that. And if I figure out how much time it takes to change my my angular position, I get a rate, the rate at which I'm changing my angular position. Okay, so what I'm going to do is I'm going to take this delta S and I'm going to divide it by delta T. And so this right here, delta S over delta T, this is, now look, this is a distance over time. What do we call distance over time? We have a name for that. It's not velocity, it's speed. So this is our speed, our linear speed, the speed at which this thing is traveling around this circle. Now I'm going to use a v for velocity, but we kind of say speed by putting a little absolute value, like the magnitude of your velocity is your speed. So we're going to call that your speed. And this is going to be equal to r. Now, delta theta over delta t. We're going to call this angular velocity. That makes sense, doesn't it? Angular velocity. And we have a variable name for angular velocity. It's this. What is that? It's not a W. One thing we do in rotational motion is we use Greek letters to represent all our quantities. And that's just a rule of thumb. It's just arbitrary by convention. This is a lowercase omega. If you really want to irritate me, you call this a W. Why did I tell you that? No, it's an omega. And what units does it have? Radians per second. Okay. Now, by the way, a radian is a dimensionless quantity. It doesn't have any fundamental units associated with it. So, but seconds is a fundamental. So 1 over, this is like nothing over seconds. So sometimes you'll see this written as s to the negative 1. S to the negative 1. What does a negative 1 mean? Well, it's a 1 over s is equal to s to the negative 1, right? Remember that from math? And so you'll see it like this. I always write it like this, radians per second, because I know radians is dimensionless, but I like to see that. And it looks more like meters per second, but it's radians instead of distance. Okay. So now if you, now this right here, this is, if you keep it delta theta over delta t, it's an average angular velocity. But if you let delta t go to 0, take the limit as delta t goes to 0, like we did with going from average velocity to instantaneous velocity, you'll get instantaneous angular velocity. I think they do it in the book. They said that instantaneous angular velocity is the limit as delta t goes to 0 of delta theta over delta t. Yeah. Okay. So this is, so our speed is equal to r omega. So this is something you need. Now, what if I make the little spot on the outside go faster and faster and faster? What if I am increasing the speed? Now that's what I'm doing here when I twist this with my fingers and I twist it. While I'm twisting it, I'm accelerating it, right? I'm making it spin faster, and it's not spinning at all, and then I twist it and it starts to spin. Well, I'm changing the speed at the outside here, and if I say, okay, at what rate was I changing the speed? I'm going to get a delta, the change in speed over the change in time. And this is going to be equal to r. R doesn't ever have a delta with it because r is a constant. But this is going to be our change in angular velocity over a change in time. And we have a name for this. Now this is a little bit different. And I'm gonna define it here in a second, but it's a little bit different than what we did before. We have a change in our speed over time. That is acceleration. But it's a special kind of acceleration. It's not centripetal acceleration. In fact, it's 90 degrees to that. This is an acceleration that changes our speed. And we call it tangential. Okay. A sub t. Well, actually, hold on a second. I'm going to rewrite this a little bit, squeeze it in. This will have to be, I'm going to call it A sub t. And this is equal to, well, r, well, let's define this, okay? The change in angular velocity over a change in time. This is called angular acceleration. Now we have a symbol for angular acceleration. It's an alpha. It's not a fish. People always call it fishy thing. Drives me. No, it's not a fish. It's an alpha. And it has units of radians per second squared. Or radians per second every second, which is radians per second squared. But since radian is a dimensionless unit, or dimensionless, it's ratio, length over length, sometimes you'll see it was written as s to the negative 2. Don't worry about that. I always use radians per second squared. So this acceleration, the rate at which I change my speed, is r times alpha. And I want you to know this. Now, this a sub t is called tangential acceleration. It's tangential acceleration. It is the acceleration that changes speed. Now, let's talk a little bit about velocity. Velocity is a vector. Vectors have magnitude and they have direction. Now, we dealt with this earlier. What do we call an acceleration that changes the direction of a velocity vector? We had a name for that kind of acceleration. It doesn't change our speed, it changes the direction that we're going in. Anybody remember what that was called? Nobody? Nobody? Starts with a C. What? Centripetal. Yes, centripetal acceleration. Oh, okay. Now, so I'm going to call that A sub C, centripetal acceleration. Now, the book calls it something different. A sub R. What do you think the R stands for? The R stands for radial acceleration. And we know what it is. We know what the formula is for radial acceleration. Now, I'm going to tell you why it's radial here and why do we call this tangential and why do we call this radial? You can use a lowercase r. I don't know. The book uses an uppercase r. What was the formula for centripetal acceleration? Equals v squared over r, right? This is the magnitude of the acceleration that is changing the direction. Look, this object is going around in a circle. So there has to be a centripetal acceleration. And that centripetal acceleration is equal to its instantaneous speed squared divided by the radius. But we have an equation for the speed. It's right here. So if we take this and substitute it in there, we get v squared, which is r omega squared over r, which is r squared omega squared over r. And so if I cancel this out, I get the radial acceleration is equal to r omega squared. Now, let's look at the acceleration on the picture. Suppose my object is, right here at the end, at its final position. The velocity vector of this this little dot, the velocity vector, look, it's going to be here. Here's our little dot, and the velocity, notice the direction it's moving in. It's always, the direction it's moving in is always tangential to the circle. Ooh, that would be cool if I taped a little arrow on there. Oh, I'm going to try it. This might not work, but I'm going to do it anyway. Little brainstorm. So this, yeah, that kind of works. All right. So this is the velocity of the object at that point. And notice that the velocity is tangential to the path. I mean, no matter where I go, if I'm over here, it's tangential to the path. The path, it's, you see that arrow? Oh, let's see. I don't know if you can see the arrow. Can't see it at all on the screen. Okay, but the path is always tangential. I mean, the velocity vector. But if I want to increase the speed, I need an acceleration that is in this direction. Like if I want this to go faster, I gotta have to have an acceleration in this direction. We call this the tangential acceleration. So the tangential acceleration is tangential to the path. So I would need there's my little a sub t right there. My tangential acceleration is increasing the speed faster and faster and faster and faster and faster and faster and faster. Whereas the radial acceleration is pointed in this direction, towards the center of the circle. It's changing the direction of my velocity vector. So so if I were to draw this acceleration, like I could have a tangential acceleration, but I could also have a radial acceleration. And notice that if I want the total acceleration, well, I could add these together. The total acceleration, I'm going to squeeze it in here. The total acceleration, well, I could make these go like this. I could put this radial acceleration over here. This drawing's getting really messy. But now my overall acceleration is the hypotenuse. I have a tangential acceleration and a radial acceleration, but they are 90 degrees apart. So therefore, to get the overall acceleration, it's the hypotenuse of this. So this is going to be equal to the square root, that is the magnitude of the overall acceleration. It's going to be the tangential acceleration squared plus the radial acceleration squared. And if you want to know what this angle is, you could use inverse tangent. And so, you can do that. I'll do one more step here. Well, what's the tangential acceleration squared? Well, that's r squared alpha squared. And what's the radial acceleration? Well, that's r omega squared. We'll square that. You get r squared omega to the fourth. Woo! So this tells you what your overall acceleration is as you go around that circle. Okay. Now again, this is linear acceleration. This is meters per second squared. It's not alpha. Alpha is radians per second squared. One last thing. if I've got an object that's spinning around, we're spinning around, the time it takes to go around once, we have a name for that. It's called the period. The period of rotation. So the period is the time for one rotation. The variable is t, and the units are seconds. Sometimes I like to go seconds per rotation. How many seconds does it take to make one rotation? Like the Earth, I think it takes 86,400 seconds to make one rotation, something like that. So it's slow rotation. Whereas this top, it's probably making a rotation once every 1/10 of a second or 1/5 of a second or something like that. Now, based on that, we have frequency. And the frequency of rotation is the number of rotations per second. Well, if this is seconds per rotation, and then I want rotations per second, I just take the reciprocal of this. Just reciprocate the period, and you get what we call the frequency of rotation. Now, a rotation per second has a name, has another unit called hertz. You've heard like a Hertz donut? No. Hertz. And Hz is how it's how many cycles or how many rotations you make per second. Now, if you make one rotation per second, you're going to get omega. Oh my gosh, this is not right. Yeah, I told my other class wrong. No, I just got it mixed up. The angular frequency is going to be a greater value. It's going to be 2 pi times the frequency. Because this is a rotation per second. Well, that would be 2 pi radians per second, which is the same thing as omega. Yeah, they're going to be confused. I'm glad I deleted that video. Okay, and so then you can rearrange this and say that the angular frequency is equal to 2 pi radians for the period, for over the time of one period, right? Radians, 2 pi radians per time of one rotation. This would be a good one to keep right here. It doesn't matter which one of these you keep. Like you should know this, and you should know this. And this is going to help us, by the way, when we get to waves. So there's a lot to this. Oh, and I left these off here. I ran out of room. Here is our overall. Are you done with this? Everybody done with this? Okay. So here's kind of an overall thing, and I'm going to staple this to the wall and so on. But I got to put 2 more on here. Well, yeah, I got to put period, which we use a capital T, and we use the unit of seconds, and then we have frequency, which we use F, and that's going to be cycles per second or rotations per second. Rotations per second, which is a hertz. Frequency is measured in hertz. So if I was to keep that consistent, just take this and put it below here. And so here you've got just about everything. Oh wait, Let's see. That should be good. Any questions? Okay, so add all of this to your equation list. Add it to your equation, and then try your homework problems. And, go through it. Make sure that you understand what the quantities mean as you're doing the problems. Don't just plug and chug. Understand what they mean. And it's actually a lot of problems I assigned, but they're pretty easy problems to do, so they won't take you that long. Okay, you guys ready? That is...
Oh.
Nice.